So how do we find the inverse of a linear transformation if we know its original matrix? Well, we want to proceed on this principle that we want the inverse to undo whatever the original linear transformation does. Right? And so the same should be true of the standard matrix for the inverse of a linear transformation. It should undo exactly what the original standard matrix did. So in this cat transformation example, if I pick kind of an interesting linear transformation like this one, say, then I can notice, for example, that what my original transformation, represented by the matrix over here, 1, 1, 0, 1, what my original transformation does is it sends the first standard basis vector, 1, 0. Right? It sends that standard basis vector to the vector 1, 0 in the codomain, and it sends the second standard basis vector, 0, 1, it sends it to the vector 1, 1 in the codomain. Right? So we know that the standard matrix of the original transformation sends E1 to the first column of the matrix. It sends E2 to the second column of the matrix. And if I'm in a higher dimensional space, it'll send E3 to the third column, it'll send E4 to the fourth column, and so on. Right? And so what should the inverse matrix be permitted to do? Well, the inverse matrix needs to do exactly the opposite of what the original matrix did. And so to find a matrix for the inverse of a transformation, what we should be trying to do, and this is what this activity is going to lead us through, is figure out how to unsend a standard basis vector from the original transformation. So let's kind of do that with this simple example first, and then we'll look at the more interesting, complicated example in your activity that you'll work on with your group in just a minute. So if I have my matrix 1, 1, 0, 1, so if that's my original matrix, then I know two things. I know that A applied to the first standard basis vector, I'm going to call it 1, 0, is going to give me exactly the first column of my new matrix. So A of 1, 0 is going to equal 1, 0. That's the first column of A. And we know that A applied to the second standard basis vector, 0, 1, is going to give me the second column of my standard matrix, which is 1, 1. So this is what we know that A does in the forward direction. So if I want to find the inverse, A inverse, should do the following. It should satisfy that A inverse applied to the first column, the first standard basis vector 1, 0. Actually, no, let's say it this way. It needs to do exactly the opposite of what this linear transformation up here did. So it needs to send this 1, 0 to the 1, 0 that it came from when we applied the linear transformation. So A inverse of 1, 0 should be 1, 0, because A of 1, 0 was 1, 0. So we just need to do backwards whatever the original transformation did. And so that means then also that A inverse of 1, 1 has to equal 0, 1. Right, so these are the two things that we need to be true for the inverse of my linear transformation. And so if I'm going to find a linear transformation that does this, I need to know what is the first column. The first column of A inverse will be exactly, according to our standard matrix formulation, will be the A inverse applied to the first standard basis vector. But A inverse applied to that first standard basis vector is just 1, 0, according to the work that we have above here. Right? So the first column of my standard matrix for the inverse is just going to be 1, 0. Let me make this a little bit bigger here. Now how about that second column? The second column will be A inverse applied to 0, 1. Problem is, we don't know what A inverse applied to 0, 1 is. We only know what A inverse applied to 1, 1 is. And so I need to figure out a way to get A inverse of 0, 1, which is what I actually want to know, it's going to be the second column of my matrix, out of A inverse of 1, 1 and A inverse of 1, 0. In other words, I need to figure out how to get 0, 1 from some linear combination of 1, 1 and 1, 0. Fortunately, this example is pretty carefully chosen. We're in like a safe space here. So I can actually get 0, 1 out of 1, 1 minus 1, 0. Hopefully that's an agreeable proposition right there. And because A inverse is a linear transformation, T inverse, or A inverse, the standard matrix multiplication, distributes across this linear combination that I have on the inside, that means that I should be able to write this very thing as A inverse of 1, 1 minus A inverse of 1, 0. And I happen to know what each of those things is. A inverse of 1, 1 is 0, 1. A inverse of 1, 0 is 1, 0. And 0, 1 minus 1, 0 is negative 1, 1, I believe. There it is. So the first column of A inverse is going to be 1, 0. The second column is going to be minus 1, 1. And so we now have all of the entries that we could want. A inverse as a matrix is going to be, the first column is 1, 0. The second column is minus 1, 1. So it's 1, minus 1, 0, 1. And there then is a matrix for the inverse of this linear transformation. So just for kicks, let's see what that inverse will actually look like. So what its geometric properties, what geometric properties that it might enjoy. So again, coming back to our cat transformation from over here, this is what the original linear transformation seems to do. It almost looks like it takes this cat square over here and it just sort of nudges the square over, sort of pushes it over like a stack of papers. This is called a shearing linear transformation. As we get into the last chapter, we're going to talk more about different words we can attach to geometry of linear transformations. This is called an example of a shear. It doesn't change the area of the square. The parallelogram over here has the same area as the original square did. It just pushes it so it turns a square into a parallelogram instead. So we would expect that the linear transformation which represents its inverse, look at that. It's a shear, just a shear in the opposite direction, right? Where the original transformation sheared my cat over to the positive direction in the x direction. My inverse transformation shears it in the negative direction along the x-axis by the same amount by which the original was sheared in the positive direction. So that seems to make sense just from a geometry perspective, that my inverse transformation is doing what we would have expected the inverse transformation to do. It's undoing what the original did. So your job is to use this similar kind of logic and apply it to this 3 by 3 matrix right here. So the linear transformation from 3 space into 3 space given by this standard matrix. This is going to lead us through the process of figuring out what vector is getting sent to the first standard basis vector by this linear transformation, because that vector is going to be the first column of the standard matrix of the inverse. And then what vector is getting sent to the second standard basis vector? That's going to be the second column of our standard matrix for the inverse. And then for the third standard basis vector, that's going to be the third column of the standard matrix for our inverse. So this is going to be a problem where you have to solve a linear system 3 times. Definitely make use of technology for doing the steps involved in this. And then at the end, you'll write out the matrix for the inverse by using your answers from parts A, B, and C. So we found the inverse of this matrix here, right? And the way that we did it was by asking for the original matrix, what are the solutions for the vectors that are getting transformed into the standard basis, right? Because the columns of the original matrix tell us how the standard basis is getting transformed out. We want to figure out how the standard basis gets transformed back. And so we use the standard basis as the right-hand sides of the equations to figure this out. And then something looks like it went wrong along the way in your calculations here. And the reason I say that, so I like part A, right? Part A asks, what is the solution to t of x is equal to first standard basis vector? You figured out that was 1, negative 5, 1. But something happened in your second and third examples, because your right-hand sides here should have been the second standard basis vector and the third standard basis vector. And it looks like what you used were the second column of A and the third column of A. And so from that perspective, your answers here are no surprise, but they are not, in fact, going to be the right-hand sides that you were looking for to determine this inverse. So just for the posterity. All right, so there was our first instance of computing the inverse of a matrix. But one of the things that hopefully you notice, or maybe you wouldn't have noticed if you use technology for the process, is that a lot of the calculations we did in A, B, and C are all the same. All that we're doing from part A to part B to part C here is we're doing the same left-hand side of my augmented matrix, just with a different right-hand side, where that 1 is just moving sort of down and everything else is zeros, because we're looking at the standard basis vectors, because we're trying to find a standard matrix for the inverse. So from this perspective, what the amount of work that it takes to find the inverse of a matrix is equal to the amount of work involved in solving 3, in the case of a 3 by 3 matrix, 3 systems of linear equations. But all the left-hand sides of that linear system are the same every time. And it's the left-hand sides that are going to determine which elementary row operations that we're going to use to discover the REF along the way. And so, as you might imagine, we could have economized the work a little bit. Rather than finding the reduced row echelon form of the left-hand side 3 separate times. If we're going to use all the same steps anyway, then maybe what we could have done, I'm going to just copy this down into a new cell here. Since all the REF steps would have been the same each time, what we could have done instead is row reduce just once, but put all 3 standard basis vectors on the right-hand sides of the augmented matrix. And so what I mean by that is that instead of finding the reduced row echelon form where my matrix is just augmented with one of those vectors at a time, we'll put all 3 of those vectors on the right-hand side of the augment bar. So if we make the choice to do all the row reduction at once, then the right-hand side can be taken to be the entire identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. Then when I do the row reduction process on this entire now 3 by 6 matrix, with the goal of bringing it into its reduced row echelon form, well, as long as my original matrix on the left-hand side of my bars here represents a bijective linear transformation, that means that its reduced row echelon form is going to be an identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. That means that by the time I do the row operations to bring A into the identity, then the identity on the right-hand side of the augment bar is going to turn into A inverse. All right, so this is the way to kind of see this as a single process to find the inverse of a matrix. Just take original matrix, identity matrix as an augmented matrix, which is now twice as wide as the original matrix, and then do the reduced row echelon form of that. And once the left-hand side is the identity matrix, the right-hand side is going to be the inverse of the thing that we started with. So we can do it all in one fell swoop if we are inclined to do so.